Hi, physics class. This lecture is going to be on energy, and I like to think of energy as the money of physics. But before we get started, I need you to go get your calculator, all right? This is a calculator and your formula sheet because this is a pretty heavy lecture. All right, so when I say the money of physics, when we look at motion, things can get complicated, right? We have, if you think about the motion, why didn't my little pointer come up? Here we go. Think about the motion of a roller coaster, right? If I said calculate everything that's going on here, you'd be like, oh man, even I don't like that kind of math. But we can just look at the energy in and the energy out, like an accounting of it, and it makes our life so much easier. And that's what I mean by saying it's the money of physics. We think about primitive economics, right? You used to do your job. Hey, everybody, don't say this to my TA. Shh, look at, those are my TAs right there. Look at them working hard. We have primitive economics. We have work. All right, do your job and you get paid in it. Chicken. And I know they say that money is the pursuit of money is the root of all evil, right? That's what they say. The second they start paying me in chickens, I'm quitting. That's it. I'm done. Okay. Modern economics, we get paid. We take this money thing, right? And that's the middleman, and then we go buy stuff. Well, it's going to be really similar as we look at an accounting of motion. This is just going to be a straight accounting of motion. So motion's hard to calculate. We have forces, acceleration, velocity, angles, blah, 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 blah. Energy is just energy in, energy out. Nice and simple. It's not a vector, it's just a number, and we can figure out how much energy it costs, right? And so that makes our lives a lot easier. Okay, when we look at energy and work, those words become complicated because they're interchangeable. Energy is the ability to do work, all right? And work is the energy transferred by a force. And I remember my first year teaching physics, trying to explain it to a student, and I realized I did a horrible job. And then I realized I did a horrible job because they are so interchangeable. Even the words we use to describe them, right? The definition of energy has work in it, and the definition of work has energy in it. But it's going to be sort of the transfer. And I think as we do the formulas, you're going to see that it's actually easier to think about. Okay. The unit for both of them is the joule, right? They even share the same units. So they are interchangeable. But energy, we're going to look at the ability to do work. And then work is when we change something. We're going to transfer the energy. We're going to do something to it. Okay. Two requirements for work to be done. You have to apply a force and it has to move some distance. So whether you're pushing something a distance or you're lifting something a distance, that's all work. All right, work, here we go. Formulas sometimes simplify things. Work is just the force over a given distance. So we apply a force for a given distance. The units for that are going to be the Newton meter. We know force is the Newton and distance is the meter. And if you want the fundamental units of that, remember the Newton was the combined units of the kilogram meters per second squared. Okay. And then you add another meter up here, and that's how you get meter squared per second squared for work. All right. Which then the Newton meter becomes another combined unit, and we call that the joule. All right. And it's scalar. You don't have to worry about direction with it. All right. It's just how much force over how far did we go. All right. Or if we're pushing a car, that's how much force we've added. If we're stopping a car, it's how much energy we remove from the car, but it's scalar. Okay. So how much work is done? Let's start doing some practice problems. We're going to lift with 3 newtons by 1 meter. Here's your equation. Work equals force times distance. Grab your calculators, and there you go. It would be 3 newtons times 1 meter, all right? If we push something 3 meters to that side and we push with a force of 1 Newton, you don't need to grab your calculator. It's going to be the same thing, all right? It's going to be 3 joules. Okay. Power is the rate as at which work is done. So the unit is power is work over time, okay? Work over time. And the way to remember this, the way I remember it, is really stupid jokes. Stupid jokes help me remember everything. My friend Power was having a really bad day. He had to work overtime. Yeah, he had to work over. Nah, I know, it's dumb. Anyway, the unit is going to be joules per second because it's work in a given amount of time. Right? So, sample problem for that, you have the net force is 2,800 newtons, accelerates a 1,250 kilogram vehicle for 8 seconds. The vehicle travels 80 meters during this time. How much work is done? And then we have time now, so how much power does this represent? Okay, so give it a try, see what you can do. Write your formula, try to get your givens and all that good stuff. Hit pause and grab your calculator. You really need a calculator to do energy. It does require a calculator. Okay, so here's your knowns. Here's your unknowns, is work and power is what we're looking for. Work is force times distance, so that was your calculation for that. And then power is just work over time, and there's your calculation for that. Okay, and there's your answer. And we can do it in, if you want joules per second, so we could go to watts or kilowatts for that. Okay. Work and energy. When forces do work on an object, the work done equals the change in energy, right? They're related to each other. So the change in energy. So if I change the energy here, right? I've lifted it up. That's the work I've put into it. That's how much work we put into it. So there's actually a work energy theorem, which states the work is the change in energy. It's how they're related. All right, potential energy. Potential energy is just the energy of an object because basically it's high up, it's elevated, and when you knock it over, it has energy and it's going to fall down. So the higher up something is, or the more it weighs, the more energy it has. And the equation's pretty simple. It's just mass gravity times height. So if you have the mass of the object, it's on Earth, you know the gravity. And then how high is it? We can tell how much potential energy it has. And you can see this is kind of easy and makes life easier when we look at all kinds of roller coasters. Just tell me how high it is and how much it weighs, and I'll tell you how much energy it has at any given moment. All right, so if something's 2 meters high, it weighs 100 newtons. We would just multiply those and get our answer, 200 joules, right? It doesn't matter if you lift it straight up or if you lift it up a ramp. Doesn't matter the path you take. This is why ramps make things easier, is you get to do the same amount of work, but you get a longer amount of time to do it in. All right, let's look at another sample problem. You're going to lift a 7.3 kilogram bowling ball from the storage rack and hold it over your shoulders. The rack is 0.61 meters above the floor and your shoulders are 1.12 meters above the floor. So you're going to take it where it was, so it has some amount of potential energy, right? And you're going to lift it and give it more potential energy. So you have the formula for potential energy, you know your knowns and unknowns. Please hit pause and get as far as you can get on this one. Okay, there's your formula that hopefully you wrote down. Fill in with your thing and the joules of it on the rack. This is on the rack, 43.6. Okay, now you've lifted it over your head and the total joules there are 80.1. And the work is the change in that. It's the change we've done. So you just subtract the two and you get the change, and it's 36.5. All right. Unlike potential energy, we have kinetic energy, which is motion. It's going to be, you're capable of doing work, but it's the energy of motion. And the formula is 1/2 mv squared. That's the formula. You're going to have to learn it, love it, live it. It'll make life easy. We have the mass of an object. If we have its velocity, we know its energy. Okay, so you would just plug in and find the joules. All right, the kinetic energy of a moving object is equal to the work required to bring that object to a stop. Okay, so if we were to do how much force times distance to bring this to a stop, we can make these two equal to each other, and we can figure out how much kinetic energy, if you have so much kinetic energy, how much force does it take to stop you, right? So When we look at kinetic energy, this is why I yell at my oldest son all the time, is he drives way too fast. And if you think about velocity, it's an exponential quantity when it looks at energy. And energy is one of the things that kills you if you crash. Your velocity is squared. So how does the kinetic energy change if you double a squared variable? It quadruples. Your energy is quadrupled. 2 squared is 4. It quadruples your energy. So the amount of work is also quadrupled, which means the amount of force to stop you quadruples. That's the property of math there. Okay. So if you're going 30 kilometers an hour and you can skid to a stop in 10 meters, if you're going 60 kilometers per hour, right? So I've doubled my velocity. What happens to the force, right? It's going to quadruple it. That's how long it takes you to stop now. This is why people always end up rear-ending people on 101, is because they don't leave themselves enough room. Don't drive in Oklahoma. They tailgate like mad there. It drives me crazy. All right, if you're going 120 kilometers per hour, which is actually not unreasonable around here, it takes you that far, right? So we are quadrupling things. Okay. Let's do a sample kinetic energy problem. You have 105-gram hockey puck sliding across the ice. Ice, why? Because there's no friction. Makes life easy. Player exerts a constant 4.5 Newton force over a distance of 1.15 meters. How much work does the player do, and what's the change in the puck's energy? So you have force, you have distance, you have mass, all right? So we have mass, force, and distance. Hit pause. We want to look for work and kinetic energy in that order. Do work and then kinetic energy. Hit pause. Give it a try. Okay. So work is force times distance, and work would be 0.675 Newton meters, right? Which is 0.675 joules. Kinetic energy equals work. So now we found work. We can use it. Wait. We can use that to find the work. From there, if we wanted, we could find the velocity of the puck. We could do other things. But at that point, you just need to use the work here is going to equal the same thing. Okay, let's do another sample problem. Kinetic energy, you have a 4-kilogram ball, transfers all of its energy to a small 2-kilogram ball. After the collision, what is the kinetic energy of the ball? Transfers all of its energy to a 2-kilogram ball. Okay, so you had a 4-kilogram ball. It's moving at 3 meters per second, and it transfers all of its energy. You just have to know how much energy it had, basically. Okay, slaves pull a heavy load. Work done by slaves is positive, negative, or 0. Work done by friction force and work done by the ground. So think about those and see if you can answer that. Okay, conservation of energy. Law of conservation of energy. In a closed system, energy can neither be created nor destroyed. It's conserved, right? And that's what we're going to use in our money accounting system here. Mechanical energy of a system is just the energy of the system, not thermal, not whatever. So it's all your kinetic energy. It's all your potential energy. And let me move out of the sum a little bit. Okay. So we have the mechanical energy of this system. As we look at it, we have a little skateboarder and he's going down a smooth slope, and we're assuming no friction here. All right. And then unpacked snow is going to slow him down. So now we're going to do some work here. So as he comes down, we are changing from potential energy. When he was at the top, he had a lot. Now he's speeding up, so his kinetic energy goes up, but his potential energy disappears. And now the work starts to slow him down, and we need to know how much time that takes. So here's the work, and then he ends up having, when he stops, no energy. Okay? So the kinetic energy before, the potential energy before has to equal the kinetic energy after and the potential energy after. Okay? Welcome to high school physics, where everything is in a vacuum and friction doesn't matter. Anywhere in the real world, mechanical energy is used. Our world, Earth, it's not really conserved. So when is it not conserved? Friction, air resistance, and those are pretty much everywhere. If the object gets deformed, it's not, energy is conserved, but it went into the deforming of the object. All those things cause it not to be conserved. All right, let's do a conservation of energy problem. You have a skydiver stepping off a 5-meter high platform. So we know he has potential energy, right? He has mass and height, and we know gravity. Ignore air resistance. What is the kinetic energy and velocity of the diver as he enters the water? So we're going to take potential energy and convert it to kinetic energy. So kinetic energy final is going to equal your potential energy initial here. You're going to start up here with a lot of potential energy, and as you fall, you have no potential energy at the bottom, but it's all kinetic energy. So we can just make them equal to each other and then find velocity. So hit pause and do it. I am going to move out of the sun again because it's following me. I think this thing's taken so long. It's just chasing me. Okay. Hopefully you did that. So reference levels, the water height, that will be when it's 0, right? And so MGH, it's 5 meters high, you know gravity, you know his weight. You find his potential energy, which is going to equal the kinetic energy final. So when you have that, you can use it, set it equal to 1/2 mv squared, and from there, you can solve for velocity. This little trick right here, what we've just done, a lot of problems are going to be just like this. I give you the potential energy, find the kinetic energy. I give you the kinetic energy, find the potential energy, right? This is very common energy problems. Okay, let's look at some machines because they make our life easier. The idea of it is that we can do a smaller force, but we have to do it for a longer period of time. That's how most simple machines work. They're all going to conserve energy, and you're going to put work in and you're going to get work out, okay? So how does it work? We're going to apply a smaller force for a longer distance, and we're going to get a bigger force for a smaller distance, and that trade-off makes it so that we can lift heavier things, right? And the lever is a nice example of this, but all simple machines work under the same principle of we're going to do something longer or farther, but we're going to have less force that we have to apply. There's a trade in life. Always there's a trade-off. All right? So if we look at a system of pulleys, block and tackle, the way this works is she's pulling up, right? Think of her pulling up. And if she pulls up 1 foot, this is only going to raise up 1/2 foot, right? It's going to give her half the distance, but that means she has to pull half as hard. So you've reduced the force you have to apply, which can be nice. You're still going to end up pulling it all up because you have to go further. It doubles the distance, but that can be okay. Okay, in the case of a simple one like this, actually, if you just pull up 1 foot, this goes 1 foot up, this thing really just changes direction. And so when we think about that, we need to think about efficiency. Some do, like, this just makes life easier, right? Because you can't get up here and pull it. But the efficiency of it is not helping you. So the energy out and the energy in is the efficiency of something, right? Yeah. And I think that's it. That wasn't too bad. Maybe it